All right, I know I said that the last one was the last video, but actually this is. It made more sense to split it. So the second concept that we'll talk about real quick is just the way that changing the Reynolds number affects what the flow does. So here's a really simple flow. This is flow over a flat plate. Once again, uniform upstream velocity. And you can imagine that any streamline approaching this plate is going to have to deflect to get around the plate and then leave out like so. If we go with a really small Reynolds number, so 0.1, what that means is that the velocity is very small, or that something about the top is very small compared to the bottom. In other words, the momentum, right, rho u kind of looks like a momentum. This is very small compared to the viscous effects, which are captured by this mu. In other words, the Reynolds number represents a ratio of momentum or inertia to viscosity. So at low Reynolds numbers, what you see is a very big region here, that very thick boundary layer affected, and so this viscous region inside which the flow is very much dominated by viscous effects is quite large compared to the plate. Outside of that region, you could almost ignore it altogether. In fact, you could pretend that this is an inviscid wall, and the flow outside of it more or less does what it would do if this was a frictionless flow around an object shaped like that. If we speed the flow up, we're going to increase the Reynolds number. So let's go by a factor of 100 here. So we go from 0.1 to 10. What you'll see is that the thickness of this viscous region actually shrinks. It gets smaller. And this has to do with the way that the flow out here is able to kind of push back in and keep things moving. And you'll see that the boundary layer now is much smaller than it used to be relative to the very slow flow. And that means that downstream the wake is smaller, and that's kind of interesting. If we speed up even farther, we get to this point of a very thin boundary layer. And in cases like this, the flow outside of the boundary layer is more or less unaffected. What we can say here is that the viscous region is very small, the inviscid region is very large. This is the kind of situation where it's still okay to use things like Bernoulli that make inviscid assumptions. So check out for, again, the fact that this is the Reynolds number. If the Reynolds number is 10 to the 7, 10 million, what you're looking at is that the momentum is very huge compared to the viscous effects. And so that's why as this shrinks, we get closer and closer to an inviscid flow that we can treat using assumptions like Bernoulli. So let's bring this in for a landing. Last little page on this. Let's do another one. This is flow around a cylinder. And once again, at very small Reynolds numbers, the flow hugs the cylinder, and viscous effects are very important because most of the drag is actually coming from there. And so this thing is behaving very, very viscously. In fact, you can imagine what this would be like is dropping, say, a marble into a bucket of maple syrup, and it would move very slowly through the thick syrup. If we speed up slightly, say a Reynolds number instead of 0.1 of, say, 50, what you start to get is this separation. What that means is that the flow is following along the cylinder, but at this point here, it lets go, and it just ignores that this is here. And so behind there, you'll get this little bubble of kind of recirculating flow, and you get this viscous region that appears that's quite large. And in fact, what's interesting is that this almost becomes like a false body. In fact, people have done some research with, could we use that to create lift, because the external flow outside of this is actually following that. And there's tricks you can do where you like spin the ball and things like that that actually make it go up. If we go down to an even higher Reynolds number here, now the flow separates even earlier, and you get these interesting little vortices that let go. You can search for von Karman, K-A-R-M-A-N, von Karman Street, and what you'll see are these little vortices that let go, and they're pretty neat to look at. What's interesting about separations around cylinders and spheres is what's actually happening. So you can imagine that a flow comes in and hits it, and as we move around the surface, the boundary layer grows. And how does it grow? Well, just the way that it would over a flat plate, except it's curved. And so you have a boundary layer, and the thickness is growing. Here it is even thicker. Here it is even thicker. But what's crazy is that because we have an external effect of, as we start moving downward here, it's like going down the back of the wing, the pressure is increasing. In fact, the pressure is increasing so much that it's killing the flow in the boundary layer and actually pushing so hard that you get this backflow. So at this point where the derivative goes to 0, this is where you get a separation. That's the separation point. And beyond that, you get this backflow, these recirculating things. So it's pretty interesting because essentially during the first half of this, the velocity is increasing and the pressure is decreasing. But during the second half, the velocity is going back down, and so the pressure is going up. The net result of that is that you get this big region here called a wake, which is where the flow is let go and is no longer flowing around the ball, and this thing called pressure drag, which is what slows things down like golf balls and baseballs. An interesting effect is that with a laminar flow, this separation happens at about 60 degrees from the leading edge, and so you get a wake that's quite large. Comparatively, a turbulent flow lets go around 120 degrees, and so you get a very thin wake. And so comparatively, you get a much lower drag if you can get this flow to go turbulent. It seems counterintuitive until you realize that most of the drag on this ball is due to pressure drag in the wake, not viscous drag, which would certainly go up when you switch from laminar to turbulent. By the way, this is why we drop dimples onto golf balls. We trick them into going turbulent to get this wake instead of this one.